The Astronomers celebrates the spirit of discovery and is made possible by the W.M. Keck Foundation, advancing the frontiers of education, science, and medical research. The W.M. Keck Foundation, investing in excellence.
For as long as we can remember, the skies have beckoned. The daily disappearance of the sun unveils mysteries in the deep of night.
You just look up at the sky and you wonder where the stars came from. And for that matter, you might wonder where everything, the atoms that you and I are made out of, came from, and everything that we have around us. And every culture has had their own cosmology, and it's simply their answer to that question. Where did everything come from? How did things start? And also, where are we going?
Today, astronomers continue the ancient quest. How did the universe begin? What incredible forces shaped it?
Can you stick that
This group of American and Japanese astronomers is preparing a rocket experiment to investigate the glow left from the creation of the universe. They hope to discover how the young cosmos became full of the stars and galaxies we see today. In Cambridge, Massachusetts, two pioneering astronomers have made a startling discovery about galaxies.
What we came up with was this remarkable picture. Each of these points represents a galaxy comparable with the Milky Way.
How did today's universe form out of the chaos of the Big Bang? Look through a window to creation, next on The Astronomers. For most of human history, this blue planet was the center of our universe. Earth formed 5 billion years ago, along with the Sun and the other planets of our solar system. All around, billions of stars, some just like the Sun, occupy our corner of the universe. Our solar system lies about 2/3 of the way out from the center of the Milky Way, our galaxy. The Milky Way is located within a cluster of galaxies called the local group. Itself only a small part of a much larger grouping of galaxies, a supercluster, which almost disappears among the billions of galaxies in the grand design of the universe. Just as the sun warms the Earth, the intense heat from the birth of the universe, the Big Bang, has left behind a faint glow. That glow is what these astronomers from the University of California at Berkeley seek to understand.
Okay, much.
During a break from a conference in Colorado, Andrew Lang reflects on the mysteries of the Big Bang.
If the universe began as a Big Bang and started at this definite time, what was there before? And why did it start? And that is, in fact, a very interesting question. And it's one that, that physicists don't ask too much because it's too hard to answer right now. And we like to stick to the simple questions.
By studying the heat left from the earliest moments of the universe, these astronomers hope to find how the chaos of the Big Bang became the cosmos we see today. Their leader is Paul Richards.
Think of yourself as a well-trained, well-equipped physical scientist, and you make all the observations on the universe that you can today. And then you ask, what must the universe have been like yesterday for it to be today what we see? You The way you answer that question is to use the laws of physics as you understand them, and you go back one day at a time. And since we know the laws of physics reasonably well, we can, with some confidence, go back thousands, 10,000s, millions of years.
Using this step-by-step process, they look back to a time when ordinary experience can no longer explain what we see.
The Big Bang is a very difficult thing to visualize because it didn't happen in any particular place. It happened everywhere at the same time. In other words, you can't be outside the Big Bang watching it happen. I think I remember seeing that on television once, a little red dot at the middle of the screen. It suddenly filled the whole screen, and that's not the way it happened. The things that happened in the time shortly after the Big Bang are completely counterintuitive. They're not things we can understand based on our ordinary experience.
How can we comprehend what scientists tell us about the origin of the universe? They tell us that water, trees, rocks, our planet, the whole universe, was once an ultra-dense concentration of matter and energy much smaller than the head of a pin. Its temperature, trillions of degrees hotter than the center of the sun. In an instant, the universe came into being. An imaginary observer would then have seen only blinding light and a chaos of subatomic particles. No solid matter could form because of the intense heat. After hundreds of thousands of years, the universe had cooled enough for particles to form the simplest atoms, hydrogen gas. By the end of the first billion years, through a process not yet understood, the cooling gas formed embryonic galaxies. Gravity squeezed. Within the galaxies, clumps of gas became so dense that nuclear fusion began within them, lighting entire galaxies with new-made stars. The intense heat from the Big Bang has diminished, but it has not yet disappeared. An invisible, faint glow called the cosmic background radiation offers a clue to the secrets of the early universe. The University of California at Berkeley, a leading institution for physics and astronomy.
Newton's law basically gives us what the frequency is.
Andrew Lang, an experimental astronomer, is a faculty member.
Whether the frequency. So simple harmonic motion, which is.
This semester, Lang lectures to undergraduate students next to his mentor, Paul Richards.
So the nucleon numbers remain the same.
While both scientists enjoy teaching, their consuming passion is experimental work on the creation of the universe.
The most dramatic feature of the universe we see today are stars, galaxies, clusters of galaxies. And so it's a really obvious question. How did they form?
Our view of the universe has changed tremendously during the last 100 years. In the early part of this century, Edwin Hubble, an American astronomer, developed a convincing argument that the Milky Way is not the only galaxy in the universe. Hubble was an expert at estimating the distances to galaxies. He deduced that the universe is expanding at enormous speeds. Other astronomers used Hubble's measurements to argue that this expansion is the result of a vast explosion, later named the Big Bang. George Gamow, a brilliant Russian-born physicist, was the first to suggest that this enormously hot explosion must have left behind some traces of its heat. In the early 50s, Gamow and his colleagues predicted the existence of this heat as the cosmic background radiation. In 1965, Robert Wilson and Arno Penzias detected this background radiation using a sensitive horn-shaped antenna. The radiation became the strongest evidence in support of the Big Bang theory. The Earth floats in a sea of this harmless radiation. It carries valuable messages about the Big Bang, but the Earth's atmosphere blocks most of the radiation out. To read the messages, we must send experiments above the atmosphere.
That's right.
Dr. Toshio Matsumoto of Nagoya University has access to Japan's growing rocket program. He has come to Berkeley to work with Andrew Lang. In their joint experiments, the Berkeley group provides sophisticated detectors. The Japanese contribute the rockets and other instruments.
Spacing, we will change the phase shift. We could measure the performance, and that should show us, whether or not it's possible.
Before you come to Japan.
Oh, we want to have the whole filter finished before we go. No, maybe the first week
You
in
have
June.
some data in May.
I think in order for this to work,
The Berkeley-Nagoya partnership acquired worldwide fame among scientists with their previous rocket experiment in 1987. The result of that experiment shocked astronomers who study the origin of the universe.
When we flew the 87 flight, the instrument worked pretty much flawlessly. And so we were able to read the results off the chart record right after the flight in a very rough sense. And we knew immediately that there was something interesting there.
Astronomers expected that the background radiation would show its energy distributed along a familiar curve of different frequencies. But the 1987 experiment measured nearly twice as much energy at two key frequencies. This implies gigantic releases of energy in the early universe at the time galaxies formed, far more energy than anyone could explain. But how can astronomers know anything about events which happened so long ago? We see the universe not as it is, but as it was. The sun, our local star, appears as it was 8 minutes ago. That's how long it takes light from the sun to reach us. When we look at the Lagoon Nebula, a star-forming region 4,000 light-years away, we look that far back into the past. The Great Spiral in Andromeda. Its light is 2 million years old by the time it reaches us. At the limits of what we can observe, quasars, we see what was there 12 billion years ago. If we could see beyond quasars, still further back in time, we would find a wall of light, the smooth, featureless furnace of the early universe. The heat and light traveled 15 billion years and has become the background radiation that astronomers today use as a link to the early universe. Uchinura Bay, Japan. A fishing village at the southern tip of the Japanese islands. For thousands of years, the fishermen here have harvested the sea. Now, scientists come to cast their own wider nets into the cosmic ocean. Since the early 1960s, the Kagoshima Space Center has been one of Japan's main rocket launch facilities. In August 1989, Andrew Lang and Paul Richards arrived for the launch of an experiment to check their unexpected results from 1987. For this flight, the Americans have built an improved detector, while the Japanese are eager to try a newly designed rocket. Two years ago, Andrew Lang recruited Berkeley graduate student Dave Alsop. Alsop has spent almost a year in Japan working on the instrument package.
In a very cold radiation shield, so it varies a lot, but it's somewhere between 3.5 and 5.
Even though the project is led by Matsumoto and Lang, much of the responsibility falls on Alsop's shoulders.
It's on the other side.
この期間はそうですが、これも我々いるから、天柄まで。
Toshio Matsumoto faces a different kind of pressure. The Japanese Space Agency expects him to have the scientific payload ready on schedule, and time is becoming a factor.
3、2、1、0。
Much to Matsumoto's relief, the testing of a rocket part, redesigned at the last minute, is successful.
In the fourth stage, after the galactic, so this time they are
But Matsumoto has something else to worry about: the local fishermen. Rocket debris might accidentally fall on their ships, so the launch must happen before the fishing season begins. This small rocket is in a race with a far more sophisticated NASA satellite to be launched in a few months. The NASA satellite will also attempt to measure the background radiation. Lang and Richards are eager to be the first with results, but there's little they can do to speed up the preparation of the rocket. The launch date is a week away. Until then, the pressure will continue to increase. So far, they are only a day behind. Once testing is complete, the instrument payload being prepared by Andrew Lang will be placed inside the rocket and cooled to several hundred degrees below zero to detect the faint heat from the Big Bang.
If the Big Bang, or the beginnings of the universe, was very, very hot, then the universe would be glowing at that time in much the way that our own sun radiates now. And in fact, we might be able to observe the glow, the relic radiation that's left over from the early universe now. And this heat from the early universe enters our instrument and is focused onto a number of detectors here. And inside each of these small aluminum caps is a very tiny flake of diamond, which has been coated so that it will absorb that radiation. And it heats up by a very small amount, perhaps only a 10 millionth of a degree. But we're able to measure that using a very sensitive thermometer and then radio that measurement back down to the ground. So it's in principle the same as if I were holding up my hand to the sun and just feeling the warmth of the sun on my hand. This is a sensitive way in which we can try to measure the same sort of heat from the early universe.
Dirt or even fingerprints could ruin the delicate measurements, so the team thoroughly cleans the instruments and their surroundings with alcohol. In preparation for launch, the scientists carefully mount the cherished instrument payload atop the rocket.
The team is working together very, very well. What's important is that you don't get over anxious and decide to fly when things are less than perfect, because you have 2 years of about a dozen people's work riding on this, and you only get one chance. So it's important to keep a cool head and not bow to pressures that, of course, are exerted to launch early, because it does cost money every day that we delay.
An umbrella is wrapped around the instrument package. Seconds after launch, the umbrella will unfold to protect the instruments from the rocket's heat and gases.
Yes, but we waited for the launcher to depart. Launcher departed at 9:42. But part of that time is driving the truck, so we have about 10 minutes. So that's less time than we had
The immediate goal of this collaboration is to explore the background radiation. But there's another purpose, the training of new scientists. Dave Alsop now stands in the same relationship to Andrew Lang as Lang once did to Paul Richards. If his years of apprenticeship are successful, he may someday become an authority on the background radiation, perhaps even a professor at Berkeley, like Lang and Richards. His apprenticeship is this experiment, a real-life training ground.
Yes, 10 minutes more.
One of the interesting things about doing this kind of work in a university setting is, of course, that the training and the development of the young people is a very, very major aspect of it.
If we were doing this with a professional crew of 45-year-old engineers and we got it right, then it would have been a job well done. But there's an analogy in Japan. Baseball is very, very popular, but the most popular form of baseball to watch is high school baseball, because the players are out there and they're not getting paid to do this. They're just really having fun, and the emotions and everything that go on out in the field are a lot more fun to watch as a result. And the analogy is pretty close. Graduate students barely get paid to do this, and they're really having fun.
Under cloudy skies, the work continues. The most repetitious and time-consuming task is the cool-down procedure, requiring as long as 12 hours. Liquid helium cools the instruments to make them more sensitive to the faint afterglow from the Big Bang. Shigeru Hayata, a Japanese graduate student, and Dave Alsop are the foot soldiers. They handle the entire procedure.
When Dave Alsop approached me about working in my group, I warned him that this would be like drinking out of a fire hose. It all happened a little too fast. and Dave, to his credit, has held up remarkably well. And I rely on him now, particularly today, for example. A lot of people are very tired, and Dave keeps a very cool head, and he's come up with some of the most creative and useful ideas of the day.
It takes a while for the pressure to decrease. When the pressure is high, it's hard to remove this. So the helium comes out.
For graduate students, low pay and long hours take away some of the glamour of studying the early universe.
It's been a difficult time because we've been really busy with the experiment. It's been behind schedule since conception, practically. And I'm working 12 to 14-hour days, 7 days a week when I'm here. So it's a lot of work and a lot of strain. It's been a great experience working in Japan as education. And I certainly wouldn't fault any of my colleagues or the surroundings for the difficulties. It's just that I'm exhausted when I'm finished with work, and I want to get a hamburger and go to sleep in my bed and take a shower, and instead they have baths where you wash off before you get in, and you have raw fish and some rice for dinner instead.
This rocket experiment could help to explain the existence of galaxies, which somehow formed from the smooth, featureless gases of the early universe. How that process began is still a mystery.
There is a puzzle that exists now, and from studying the background radiation, which is coming from the very early universe, what we can tell is that at a time of a few 100,000 years old, the universe was very, very smooth and really featureless. All that existed was a diffuse gas, and there weren't any stars or galaxies. But if we look around us today, the universe is a very complicated place, and it's organized into galaxies. Those galaxies tend to congregate into clusters, and those clusters are congregated into even larger structures. And the question is, how do you get from just this gas, which is completely featureless, we think, to the very complicated distribution of matter today? All of that had to happen somewhere between the time when the universe was a little less than 1 million years old and the time when it was about 1 billion years old. And no one understands how that did happen.
There is a great gap in our knowledge of the universe, a cosmic dark age from which we receive no light at all. The background radiation may be the only clue to that dark age during the first 2 billion years after the Big Bang.
So that's a mystery. And one of the ways that we hope that we can attack that is by studying the detailed properties of this radiation that had to come through that epoch, that dark period, to reach us today.
The day before the scheduled rocket launch, a typhoon arrives. Low-level crosswinds arrive with the storm. Reports from the meteorologists are discouraging. A crosswind during launch could throw the rocket off course.
It's typhoon season here now, and we scrubbed once a couple days ago because of the bad rain, and we'll probably have to forfeit tomorrow also. So we're looking now at a flight 2 days from now, which will be about 4 days after the original schedule, but that's not so bad. Our crew is holding together quite well. I think the real pressure here is that if our instrument doesn't work, there are 100 people watching and, more importantly, waiting on us. And you can't hide if something's not working. Everyone knows about it immediately, and it's very, very costly to postpone.
Along with the bad weather have come last-minute technical problems with the instrument payload. They are now 8 days behind schedule. Matsumoto is under heavy pressure from the Space Center to have the experiment ready for launch. The skies have cleared. A balloon is released to test the winds at low altitudes. The fishermen have agreed to stay in port. The rocket could be launched tonight. Though the astronomers would like more time to test their instrument package, they decide to proceed with the launch. Despite the risk of failure, they feel they cannot afford to delay any longer. Rocket flight lasts only 10 minutes. 55 seconds after launch, at an altitude of 44 miles, an explosive charge opens the nose cone. Soon after that, the umbrella unfolds and the delicate instruments that measure the cosmic radiation are exposed. Minutes later, the instruments begin their descent into the atmosphere.
Stopper is working. You got stopper.
The colored lines are measurements of the background radiation in different channels or frequencies. They are the signature of the creation of the universe.
Hey, look at this. Look at these signals. They're great. It's quiet.
Oh, God.
We got signals everywhere. That's just fantastic.
It's relieving to actually launch it. I was worried there for a while. It's great to get real data. I mean, you sit and you think for 2 years as you build the experiment, what's going to happen? Is this really going to see the light of day or the sky? And it's just very exhilarating to actually measure something.
So what's weird is these calibrators, and in fact the temperature doesn't change very much, but these calibrators are very similar, right? So
The payoff for 2 years' work is the chart paper on the floor. For a few minutes, nothing else exists.
something just stops. Okay, and then everything's going along, and then this will be open valve. Yeah, so this is open valve here. Okay. Boy, that'll start with you.
No kidding. The performance of the instrument wasn't perfect. We got a little less data than we'd like, but the data we got looks very good indeed. In fact, it's much higher quality, I think, than our last rocket borne experiment. So that really paid off, and we've found out what we wanted to know, I think, about the sky, although that we'll have to wait until we analyze the data a little bit more.
Not so bad. We have good results found. Not complete, not perfect, but I'm pleased with that. Yeah. Not so bad.
As the hours go by, some of the measurements seem puzzling. Has something gone wrong? Or have they discovered something new about the universe? Lang and Alsop will leave Japan with a handful of computer tapes that will require months of analysis. With luck, they will resolve the conflicting measurements of the background radiation. However, one thing is clear about the radiation. It tells us that the primeval gas of the early universe was as smooth as a blanket of new snow. No features, no variations, no structure. As time passes, the smoothness disappears, and the snow begins to show features. For astronomers, the mystery is how galaxies ever formed from the smoothness of the early universe. Some answers may be found in the work of two trailblazing astronomers working in Cambridge, Massachusetts, home of the Harvard-Smithsonian Center for Astrophysics. Here, Margaret Geller and John Huckra attack the mystery of how galaxies form, not by investigating the background radiation, but by making maps of the galaxies we see today.
One is not going to explore the whole universe because it's enormous. In fact, it's really hard even for those of us who work on it directly to imagine its size. So what we do is we pick out something we can do to try to start making this map. We pick out something, a small piece, to start the process. And what we've learned in starting that process is that there are patterns. There are things that you can describe. It's not just an uninteresting random distribution of galaxies. There are striking patterns, and that makes it exciting, and it makes you want to know more.
These maps made by Geller and Huckra show that, contrary to what astronomers had believed, galaxies are not distributed randomly. Instead, they show complex patterns and structure.
The structures that you can see in these maps that we have, these are circular slices of distributions of the galaxies around us. In both of these maps, we're at the center of the map. Okay. You can see some very dense, sort of finger-like structures that are pointed right at us. This one here happens to be the Virgo cluster. You can also see the large empty regions, the voids, almost circular in shape in many of these things, which in fact occupy most of the volume of the universe. Most of the universe is not particularly densely filled with galaxies, but 80% or 90% of the universe is fairly empty.
The question of galaxy formation has always puzzled astronomers. Now they face a still larger problem trying to explain these enormous patterns. From ancient times, skywatchers have identified patterns in the heavens. For thousands of years, celestial maps were two-dimensional, showing only latitude and longitude. Early sky charters had no way to find the third dimension, the distance from Earth of each individual object. To make a truly three-dimensional map, Geller and Huckra have obtained the distance from Earth for more than 11,000 galaxies. For each galaxy, the process begins with a trip to the basement of the Center for Astrophysics. They find each galaxy to be plotted on a two-dimensional photograph of the sky. On these negative pictures, galaxies and stars appear as dark dots on a light background.
Here is 956 plus 1927. 0956 plus 1537.
The overlay provides the name or number of the individual galaxy and its location in the sky. Huckra takes a series of photographs of small regions of the sky survey. At the observatory, these photographs will be used to identify the galaxies seen with the telescope. Like other astronomers, Huckra hopes to resolve the apparent contradiction between the patterns of galaxies and the smoothness of the early universe revealed by the background radiation.
The data that exists in a lot of different forms, cosmic background radiation, the galaxy distribution, everything all like that, are not particularly doing very well with respect to one another. There's something that's missing from the way we see the universe. And I suppose my hope as an individual is that by making observations, maybe we'll find the missing link, the key that will allow us to unlock this puzzle.
At Mount Hopkins in Arizona, Huckra is on good terms with the 60-inch telescope. Huckra hopes for clear nights when he can observe up to 30 galaxies. His personal record is 62, observed during one long winter night. Huckra carefully analyzes the light from each individual galaxy to estimate its distance. In Cambridge, Margaret Geller enters the distances into a computer to produce a three-dimensional map of galaxies. After selecting an area of the sky to map, they draw an imaginary slice or wedge starting from the Earth. The slice reaches hundreds of millions of light years into space, large enough to contain thousands of galaxies. Geller and Huckra use their distance measurements to build a three-dimensional picture of how the galaxies are distributed in the slice.
When we had finished the first slice, we saw a remarkable pattern, which looks like this. And what are we looking at here? Well, our strip across the sky runs like this. And we sit here on the Earth, and we look out 450 million light years into the universe. And each of these points represents a galaxy comparable with the Milky Way. So each of these points, each of these 1,100 points, is a galaxy containing billions and billions of stars.
The first slice of the sky, made in 1985, surprised astronomers with its complex patterns and unusual shapes.
Now, you can see that there's a remarkable pattern in this plot, that the galaxies aren't just randomly distributed. It's a pattern you can look away from and remember. In fact, many people describe it as being a little man. You can see his torso here and his legs. But more generally, what you see is that there are regions where there are very few, if any, galaxies like this, and we call these voids. These are huge dark regions, 150 million light years across, and there are thin structures where the galaxies lie. And you can see that you see these apparently coherent structures which thread all the way across the survey. And when we map other slices, we can map slices to the north and south of this. We see this structure again and again and again. So it turns out that it's a huge sheet, and it's the structure we call the Great Wall.
The Great Wall is the largest known structure in the universe. A loose pattern of galaxies that arcs 500 million light years through space. The astronomers have continued adding slices to their original map. The new slices show that the patterns continue to an enormous depth. During a tutorial, Margaret Geller explains the map to a group of Harvard students.
So now what we're going to do is build up the survey slice by slice and just stop when you think the structure matches.
A student brings the second slice down on the computer screen. All the slices show the immense patterns of galaxies that surround nearly empty regions of space, hundreds of millions of light years across.
And what you see is that there are very large regions which are dark, and that the galaxies are in thin structures which surround or nearly surround them.
What unknown forces in the early universe could have created these vast structures?
The problem with these patterns is that they're enormous. So the universe now has large irregularities, very large irregularities, much larger than people had expected. And we think we know that early on the universe was very smooth.
Somehow the smooth early universe evolved into these enormous patterns. Could titanic explosions after the Big Bang be the cause? The answer may be hidden in the cosmic background radiation. In Berkeley, California, a thorough analysis of the data from the 10-minute rocket flight is being made by Andrew Lang and Dave Alsop. Their goal is to check the results of their previous rocket experiment in 1987 that had measured more energy than expected, suggesting large energy releases after the Big Bang.
A couple of days before the launch, about a week after the time we were supposed to launch, and running through this calculation in our heads, I mean, it's pretty close.
Yeah, it was like 10 or 15 minutes. It was not, I don't think it was 3. I mean, this is.
They now know that electrical interference from other components inside the rocket contaminated this latest experiment. For 2 months, Alsop has struggled to overcome the problem.
I can show you what the phases look like over here.
Yeah, let's take a look at that.
Alsop is trying to extract usable data about the background radiation from a sea of electrical noise.
You can see in the low frequency channels that have a lot of cosmic background signal.
Yeah.
It looks like things are fairly good in most of the channels, the higher frequency channels, which really probe the excess we were interested in. We have problems with data that has added signal, and that we don't know what that added component is. So we have to try to.
The Berkeley group knows it's in a race against a far more sophisticated satellite called COBE, the Cosmic Background Explorer, about to be launched by NASA. At the Goddard Space Flight Center in Maryland, COBE is being prepared to make the most comprehensive measurements yet of the cosmic background radiation. The 2-story COBE satellite includes a heavyweight version of the experiments launched from Japan. Instead of the 10-minute flight of a rocket, COBE will spend 2 years in orbit. The chief scientist for the mission is John Mather.
This is the Cosmic Background Explorer satellite here, the COBE satellite, which is intended to observe the Big Bang of the universe, something that happened 15 billion years ago. This is the helium cryostat in here in the middle, and it's extremely sensitive to heat. The sun actually shines in from the side here and lights up these solar panels, which will provide power for all of the instruments and the transmitters and tape recorders and everything that we have on board. 700 watts it takes to run this spacecraft. And on the bottom, where I have my hand, is a place for a transmitter antenna that will send the data back down to the ground. That'll come down once a day.
John Mather has spent most of his career working on this project. In the early 70s, just out of graduate school, he helped write the original proposal for the COBE mission.
Changed the mirror mechanism on the fire assay.
COBE has 2 main tasks: First, if the extra energy in the background radiation measured in 1987 by the Japanese rocket exists, COBE's sensitive instruments will find it. COBE will also search for deviations from the smoothness of the cosmic background. These deviations could be evidence of the seeds of primeval galaxies.
We're looking back at the Big Bang itself, which people used to think was an extremely smooth and simple sort of Big Bang, no features, no anything. And yet, when we looked into it, we found that this was one unusual example where, at least according to theory, there has to be some kind of primeval seed, some kind of primeval structure that would lead to the present-day structures that we see, where there are galaxies here and there, and there's a pattern of them. Galaxies are clustered in groups, and the groups are clustered in superclusters. And all of this is very much not random. So somehow we need to explain this present arrangement in order to understand how it all came to be. And we're trying to push our boundary of knowledge, our uncertainty, back as far as we can in time. And we can come pretty far back, but it's a long ways back to the Big Bang.
Once COBE reaches orbit, 560 miles above the Earth, it will deploy its thermal shield, solar panels, and antennas. About a week after launch, the cover will be ejected, and the instruments will begin to measure the background radiation. November 1989. Before dawn on the day of COBE's launch, Paul Richards joins his former student, John Mather. 20 years ago, they worked together on some of the first background radiation measurements.
At that time.
At the Western Space and Missile Center in California, a group of collaborators anxiously waits.
5, 4, 3,
The morning of COBE launch, I was mostly thinking about, is this thing really going to work? Is that rocket going to blow up out there, as some rockets have? And is all of our efforts for all these many years going to go up in smoke? Mostly I was just thinking, well, there it goes.
Congratulations, you survived the launch.
Yes, I did. Thank you. It's a wonderful feeling. We expect to see such a vast amount of data that it's just going to take us a long time to process it. And I think it's quite likely that Paul and his crew will be there first with the more immediate results. And we're certainly very excited to hear what it is.
The important thing in the long run is not to be first, but to be right. And the incredibly complete data gathering capability of COBE greatly enhances the probability of getting the right answer.
January 1990, Aspen, Colorado. This famous ski resort is also home to the Aspen Center for Astrophysics. This year's annual winter conference focuses on the early universe, with special attention on the cosmic background radiation. Experts from around the world are eager to discuss results from COBE and the Berkeley-Nagoya collaboration. There's an active rumor mill speculating on who has succeeded and who hasn't.
Sort of had this bottom level of ionization.
From the cosmic folding sunshade to actually help lower the temperature.
On the first morning, astronomers hear John Mather's talk. COBE has been in orbit for 2 months. It's working perfectly and hasn't detected evidence of primeval galaxies in the background radiation.
comes in from the side, and the satellite...
In the audience, Andrew Lang, Dave Alsop, and Paul Richards have a personal interest in what John Mather has to say.
Actually, the CN measurements are here, and the Matsumoto and Lang measurements are here. So we're not consistent with them, but we're consistent basically with the other longer wavelength measurements. I think one thing...
One brief statement from Mather ends 2 years of controversy. The 1987 measurements by Matsumoto, Lang, and their collaborators fell above the curve predicted by the Big Bang theory. Kobe's multiple measurements confirm perfectly what most theorists think about the Big Bang. No one doubts which scientific team has made the correct measurement. The Kobe satellite wins persuasively through the volume and precision of its data. That evening, Andrew Lang announces the results of his rocket experiment.
Give Andrew their undivided attention.
Well, Dave Schramm concluded his talk. His final conclusion was the bump exists. And I guess I'm going to spend some time talking about a bump that has a slightly more questionable existence in the last week or so. We're not done with the analysis. There was a tremendous amount of electrical interference during the flight. It's complicated the analysis a lot.
Lang's bump is the extra energy he thought the 1987 rocket flight had detected.
With an efficiency of about 10 to the minus 3 at a redshift of about...
Kobe has shown there is no bump, no gigantic explosions after the Big Bang. In science, such setbacks often face those who advance knowledge by taking risks. Nevertheless, Lang feels the sting of disappointment.
I think everyone in the field knew full well that there was a good chance that the result was wrong, particularly because the result itself was rather extraordinary and was really very difficult to explain by any cosmological scenario. It was very exciting for the theorists, but a little implausible. And I think so. I think that the conservative faction in the field always took it with a grain of salt, as did we, which is why we mounted as quickly as possible another rocket-borne experiment to go out and check it.
We busted a gut to fly a second time with a much improved apparatus to check this result before anyone else had a chance to look at it. And unfortunately, the experiment was contaminated by electrical pickup, and so we were not successful. To me, that's the real disappointment. I'd have loved to cross-check that result. It was sad that the Kobe people got to cross-check it.
It's somewhat disappointing, personally, because it would have been a lot of fun.
Really jazzy.
You know, but that's not science, you know.
Most of the things that revolutionized the worldview turn out not to be so revolutionary. And so if you have a long scientific career, you go through these things several times, and then you anticipate that they might occur. But that must not stop you from trying to do good work.
Exploring the early universe has made a close-knit group out of these astronomers. Nearly all have worked with Paul Richards, which makes this a special moment. For this group, Kobe's success is a landmark in scientific history.
I think if you really think about, though, how many serious close calls we had with the Kobe, you wouldn't really start asking for less reliability.
A toast to the 3 people who were at this table who would have really taken the heat if it didn't work. It's a small group of people who participate in experimental and theoretical cosmology, but it's large in the sense that it really is a community. Nobody does this alone. People work in collaborations, and then those collaborations interact very strongly with others.
There are many roads to scientific knowledge. Experiments can be large or small, rivalries intense or friendly. In this case, the cross-checking of results by competing teams has yielded slow but steady progress. Theirs is a new field of astronomy, full of promise.
I'd like to toast Kobe for making the 90s a very exciting time. So, here. Big toast.
All around us in the cosmos lie star-forming regions, their light laden with the secrets of the birth of stars. Beyond them lie galaxies of many different sizes and shapes. From even farther comes the cosmic background radiation. After traveling 15 billion years, it may tell us how the perfectly smooth young universe developed galaxies of such different forms and shapes, and why galaxies are arranged in such enormous, intricate patterns. If we find these answers, new questions will arise, for our curiosity is as large as the universe.
This is PBS.